Good evening. So today we are going to look into the application of statistics in data science. So the first question that we face is why do we learn statistics, and what is the importance and application related to statistics in this data science? So these are the points that we have here. So with the technological developments and revolution of internet and social networks, data generated from electronic devices produce large amount of data. So nowadays we have, so much revolution over the internet and the social networks, and also the tracking that we do in terms of collecting the data. So that actually gives us a lot of data, lot of amount of data, which can be studied for further progress. Or as we say, the statistics is actually the art of learning from data rather. So in that way, so similarly we have any business or management needs quality information to make informed decisions from further analysis, study, and research. So all that can be done for using statistics. What is the purpose of uh, what is the purpose of analyzing all this data? So basically, so that will give us the opportunity to create a better and efficient world tomorrow. So where we will be able to effectively process and analyze large amount of data using our computing power. So this computing power is what it comes from the data science aspect, and the pathway or the road that we are heading to. So that is gets guided from statistics. Okay, so these are the few importance of statistics in different fields. So of course, better data visualization from business intelligence. And how do we do it? By discovering patterns or trends from data, with organizations gain competitive advantage in the marketplace. Also using average, dispersion, and estimation allows us to come up with the conclusion that are closer to real answers than just taking a wild guess. So there is two aspects basically. There are two aspects here. So the first one is that it's necessary to discover patterns and trends from the data. So which will be the visualization part, or maybe the organization of data. And the other one is using these data, we can actually try to predict for the better future. So here we have the estimation part, right? Okay, so these are the fields actually where statistics holds a central position, and that includes industry, commerce, trade, physics, chemistry, economics, uh, all these. So application of statistics is very wide, and yeah, so there can be a few more examples related to these fields and how they are actually being applied. So like if we take biology, so there is a different segment of statistics which is known as biostatistics, where we actually study the combination of genes and meta-analysis or efficacy of a drug. So all this actually comes in this section of biostatistics. Similarly we have statistics in physics, in chemistry, and other fields as well. Yeah. So from there here, where we actually want to take a closer look, with the real answer than just taking a wild guess. So for this, we can refer to the example of stock market, or maybe weather prediction. So all these things can be, attached to this estimation part. Yeah. So moving on to the next slide. So now the types of statistics. So there are majorly two types of statistics. I mean, statistics can be divided broadly into two sections. So the first part being descriptive statistics, which is concerned with the data summarization, graph, charts, and tables. And the other part, which is the inferential statistics, which is the method of about predicting the population parameter from a sample. So which involves point estimation, interval estimation, and hypothesis testing. So in general, there are two sections how we look into the statistics. So here in the first one, we actually can summarize from the graphs or the charts or the tables coming from the descriptive part, and using all the information here we have under inferential statistics, we actually try to estimate the population parameter from a sample. So yeah, so we are going to look into that later on deep down, because there are a few terms coming in now, so such as population, parameter, sample. So all these things are what we have to understand. So formally, descriptive statistics describes data, for example, a chart or graph, and inferential statistics allows you to make predictions or inferences from that data. So with inferential statistics, we take data from samples and make generalizations about a population. So this is where this estimation comes into play, where we actually look into the data collected from sample and we try to generalize the outcomes or the results for a whole of the population, right? Okay. So next we have population versus sample. So what is population and what is sample? So population is the collection of all possible observations of a specified characteristic interest, and sample is a subset of population. So suppose if I want to know what is the mean height for the whole of the country, say India. So what is mean height of India? So here India will be referred as the population. And for that, if we try to predict what is the mean height for India, we can take out samples. Now there are ways to actually take out samples, of course, which we can look into uh, under sampling. So we are not getting into that. So there are some predefined ways to look into the process of sampling. Of course, there are a few principles and ways how do we take out samples from the population. But generally, if we consider a subset, few of the subsets which from the population, so that can be referred as the sample. Now, few more thing is that for a population, this characteristic of interest is something which is unknown and which will remain unknown for its in its true sense. So the true value is something that we will never be able to find accurately. So for that, we only have the other option to estimate it rather. So what happens if we so what happens if we try to study all the constituents of a population or all the data points in a population? So by the time we start from one end, and by the time we reach half of the population, the previous constituents will get to change. I mean, some people will die, there will be newborns. So the constituent of the population, that will actually change. So it's really difficult in terms of coming up with the true value of a population for the specified characteristic interest. So instead, what we do, we take out samples from the population, and here we have finite number of observations in a sample, where as in population, we have infinitely large number of data points in a population. So for a sample, we will be able to study, all the characteristic of interest that we want to. So supposedly, if we want to find what is the mean height for a sample, so as because the constituents in the sample is finite, so that way, we will be able to find the true value for the sample. So the average mean height that can be found from a sample accurately. So on the basis of those known values, we will try to estimate the unknown, which is the average height for the whole of the population. And this idea will lead us to the concept of statistic and parameter. So a parameter is something which actually characterizes the whole of the population, and a statistic is something which gives us some information about the sample, right? So a parameter is something which is unknown, whereas a statistic is something which is known, as because it has finite number of observations into the sample.
Pratyay sir, I
Yeah,
have one question.
yeah,
Now, when we come to sampling,
yeah.
right, and as a data scientist, right, when we have to do the sample analysis, how is it? Are there going to be specific formula? Like earlier, right, you just mentioned that
Mhm.
right, sampling has altogether different set of rules.
Yeah.
Will those rules will be right into formulas, and then like we will be able to sample the data that we are getting?
Yeah, so there are different methods of sampling. So, so to start with, the simplest of them will be simple random sampling. So where we actually randomly sample from the population. Now, there can be some other characteristics as well, which we want to preserve while we do the sampling. So for that, we can have cluster sampling or maybe a stratified sampling. Even for our college projects, somewhere where we actually have to come up with the data, and it's not quite possible for us to reach out to the population and frame the sampling correctly. So there we often use a sampling which which we can actually. So in that way, the sampling can be of many type, and yeah, for all of them we have different wayouts and different methods, and yeah, and different formulas associated with the sampling procedures as well.
Okay. So now when the clustered sample is created,
Yeah.
how does it differentiate between with other sampling? I mean, is there any reasoning that we need to do, or any purpose like to select specific samples?
Yeah, 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 of course. So, I mean, cluster sampling can be referred when, we see that there is some sort of a clustering or clustered data into the population. So we want the sample to represent all those clusters that we have. Say
Hmm.
very bluntly, if we speak about, say the example that we were referring to previously. So if we want to find the mean height of India, so maybe there are sections of India where we have, shorter people, where we have much taller people. Maybe in Punjab side, we have much taller people. Into the northeast, we have, very short people. So as because we are trying to, so sample should be something, which will be able to represent all the population constituents in a
Hmm.
greater way. Yeah. So in that case, we will have to see that how the data is clustered. So, and whether all the from all the clusters we are being able to represent a few of these like data points into the sample. So
Okay.
in yeah, so that is how clustering actually we look into clustering
Okay.
sampling. Yeah.
Okay. And the other sampling you were telling about was what? One was
Yes.
cluster sampling, and there was
Yeah,
one
I
more.
got started with the simple random sampling, so which is actually the probabilistic sampling. So where every individual in the population or all the data points in the population has the same probability to get included in the sample. So as like what we do in simple random sampling. So if there's say if there are 5 balls in a bag or in an urn of different colors, say 5 colors. So if I want to choose like 3 of them, so all of them are having like equal probability to get selected into the sample. So in that way, like this is something what we have as simple random sampling. Now even that can be with replacement or without replacement. Other than that, I've spoken about cluster sampling,
Hmm.
and yeah, so there was one more which is convenience sampling. I mean, that is what we do, in terms of handling college projects. So according to our convenience, we go to people and ask them to fill up our questionnaire. So that is what we call as convenience sampling. And there is this other which is stratified sampling. So where we actually divide the whole of the data into different strata, and then we try to do some sort of a mechanism to convert them into samples.
Oh, great.
Yeah.
Yeah.
So
Thanks.
yeah, sure. So I mean, the basic purpose for this sampling is as because it's very much impossible for us to come up with the true value of the characteristic interest of the population, which is the parameter. So that's why we have to estimate the parameter using the the sample, the known information, basically. Okay, so let's just move. Yeah. So yeah, so let's just look into the next slide. So here we have this parameter versus statistic thing. So in research, a population is the entire group that we are interested in studying. This may be a group of people, example, all adults in US or employees of a company, but it can also mean a group containing other kinds of elements, objects, events, organizations, countries, species. I mean, whatever characteristic of interest that we want to study. So what is a sample? So a sample is a smaller group taken from the population. So of course that you see that this person got chosen into the sample, maybe this person got chosen into the sample. So likewise, so there are so the process of sampling basically denotes that I mean that actually I mean that will that defines the process, that how these selections will be done. So that is what comes under sampling. So but in general, so if we have to consider a sample out of a population, so the sample is the group of elements that you will actually collect the data from. So this is the data we actually get to study, taken from a population by some mechanism, which is sampling, which we are going to look into the later half of this course. So next we have what is a parameter and what is a statistic. So a parameter is a number describing a whole population, example, a population mean. And while statistic is a number describing a sample, which is a sample mean. So if we want to study the population mean, so likewise, in the sample, we have to look into the same thing. So that's why, sample mean is something on the basis of which we will try to predict the population mean. Suppose if you want to know what is the population sum total, sum of the population. So for that, of course, we have to study the sum total in the sample. So likewise, we have to, look into the same thing in the sample as well, which should be an unbiased estimator in terms of predicting the population parameter, right?
Okay, so
Yeah,
it like what I'm understanding is like if there is entire population, that will be the rule. Like it will be set as a parameter,
yeah,
right? And they'll say that okay, this parameter is applicable to the entire population.
yeah.
And when we come to uh, sampling, it says that okay, this sample is based on the statistics, and according to that, the what do you say, the
Yes,
prediction is.
prediction, exactly. Yeah. So it's basically just that I mean, like what we do, in our daily life. So on the basis of the known information, we try to predict something which is unknown, right? So the first thing that we need to understand here, that why this parameter is something which is unknown. So it's unknown because it is really impossible to find its true value. So what is the, say, the average mean height of India? Now every moment it's changing. Some people are dying, maybe there are newborn cases. So every moment it's fluctuating. Same for GDP of the country. So every moment, some people are gaining money, some are losing them. So there are fluctuations in business and contributions towards the growth of the country. So but then why do we need this parameter? So if you want to do business, with some other population, suppose if there is some sort of a business transaction with some other country, say USA and India. So we need to track, what is the GDP of both the countries, so that we can uh, I mean so that we can I mean, introduce the taxations and all the other financial, parameters that we have in order to deal with, the difference in the economy. So that's why we need some sort of suggestive value, with which we can actually work. So if someone, so if we are talking about, say, people in Canada, so then readily we will have some sort of an idea that yes, the Canadian people are much taller on an average, than Indians, right? So, but so how do we get to there? So for that, we need to have some conclusive value, which will be a parameter. But of course, that's really impossible to find the true value of the population. So that in that way, what we try to do is we try to predict using a statistic.
Okay.
Right? Yeah.
Yeah.
So now whether so one more aspect of looking into a parameter is that is this a variable or a constant? So whether a parameter is a variable or a constant. So that is one more aspect. How do we look into parameter? So because it has got some variable property as well, but it is actually a constant. So we can say it's a variable constant. So I mean, for in reality, it's always a variable. Of course, the value of the parameter is something which is fluctuating every moment. But with that fluctuation, we won't be able to do business, or we won't be able to represent the attributes of any country, uh, or any progress, or whatsoever we have there. So for that, we need some value which is a constant. So a parameter has got a variable nature as well as a constant nature, whereas in the value of statistic is actually a constant, because we have a finite number of people into the sample, so that value won't change. So say if for say in a school or college, say if we consider a class or a section of students and find their mean average height out, so that won't change unless or until I change the constituents of the sample. But on the basis of that, if you try to predict for whole of the population, say on the basis of a class, we try to predict the whole of the college, what is the mean height of the whole college, so that will be population. Okay, so is there any clarification that you need, or any concerns related to whatever we have looked into so far?
Uh, Perfect, I think.
Yeah. Okay. Yeah, so let's just look into the next one. Now there is one more thing other than this estimation before I go to the next slide. So which is census, right? So in census, what we do, we basically consider the complete enumeration of the population. So other than sampling procedure, there is this another process which is complete enumeration. So in complete enumeration, we actually study the whole of the population and all its constituents. Now, of course, like what it happens for census, so each and every after 10 years, the government actually I mean, runs this census where they track, I mean, different information related to the number of people, and a few more attributes in terms of the information they need to run our government, right? So in that way, so in census, we basically consider each and every, we try to consider each and every individual, but it might well happen that maybe someone got double counted, or maybe someone was on the road traveling, going to somewhere, so few of the people got missed out. So there are situations, and there are procedures how to deal with that as well. But in general, yeah, I mean, the whole of the population actually gets covered in terms of collecting the data. So that is known as the complete enumeration, right?
Okay.
Yeah. So next we have a few notations about the population and sample. So in statistics, we have different versions of the same thing under the population and sample. So this symbol, which is mu, so that represents the population mean, whereas X bar, this represents the sample mean. Similarly, we have the population variance as sigma square, whereas the sample variance is denoted by S square. And then you have sigma, as we know that variance the relationship between variance and standard deviation. So basically standard deviation is nothing but the root over, positive root over of this variance. So this sigma is the standard deviation for the population. So see, as because we have had sigma square, now we have sigma. Similarly, we have S square, and now we have S for the standard deviation. Sorry. Yeah. And this is, yeah.
One quick question.
Yeah, sure.
The sigma symbol, is it available on the computer as well? I mean, on the laptop, or right? Like we usually, when we have the keypads of the
Mm-hmm.
when phone or anything, that there are like certain symbols. So
Yeah.
within the symbols, are they available on the
Yeah.
laptops?
Yeah, in Microsoft Word, I mean, there is this provision of getting sigma, and there are few other softwares also, or applications which actually let us type in all the mathematical notations, say such as math type. So
Hmm.
using those, we can actually write down all the symbols.
So like when we are using, for example, NumPy or in statistics, I mean in data science, we should have all this symbol ready.
Yeah, there we can actually define them. So in
Mhm.
words, we can write them, and there are different spaces where it is implied that, positional reference rather. So where we can specify the value of sigma and all the, parameters that we will get to deal with. So yeah, accordingly, we can use them.
Okay. Uh,
Yeah. Yeah. Okay. So these are the symbols. So moving on to the next slide. So now we should look into the types of data. So, so data can be broadly classified into two sections. One is qualitative data and the other one is quantitative data, right? And furthermore, quantitative data. So let's just cover quantitative data first. So here we have discrete data and continuous data, right? So a few examples are there for discrete and continuous as well. So the number of students in a class, so that is discrete. The number of workers in a company, the number of home runs in a baseball games. So all these are examples of discrete data, whereas in under continuous data, we have height of children, say the square footage of a 2-bedroom house, the speed of cars, like that. So the basic idea to distinguish between discrete data and continuous data is that a discrete data actually takes values which are in whole numbers, so integer values. So the number of students in a class, so that can never be in decimals, or maybe the number of workers in a company, so that can never be in decimals, right? So that is the idea how we differentiate between discrete data and continuous data. So similarly, say number of items in the fridge, so or maybe number of people in a family, or the family size, so that can never be into decimals. So all those are examples of discrete data. Whereas in continuous data, height of children, or any measurement, right? So that can take values till decimal places. And even if we consider up to 2 decimal places, suppose, say, if I refer to, say, my height is 174.35 centimeters. So it's just that I've been considering, I mean, 2 places after the decimal. So it's like 35291120 and on and on and on, right? So there is this sense of continuity here in terms of the measurements. So that's why they are referred as continuous data. Similarly, for speed of cars or any measurement, right, which can take up to decimal places, so that can be referred as continuous data. Okay. Yeah. So next we have qualitative data, so which can be divided into majorly two parts: nominal data and ordinal data. So nominal data. So for this, we have examples of gender, hair color, ethnicity. And for ordinal data, we have first, second, third, letter grades or economic status and all. So now there we have something which is, side by side, what we can, the another aspect to look into the same thing will be the idea of variable and attribute. So a variable is something which varies, from person to person or identity to identity or address to address and takes some values, right? Which is numeric and varies according to identity to identity. So my height will be somewhat very much different than that of yours. So that way, so it is variable. And the other thing is attribute, which is also something varying from identity to identity, but is not numerical, non-numerical, right? So that is known as attribute. Say my favorite dish can be very much different from yours, but that is not something which is quantitative, right? So which is a qualitative data. So that is known as attribute. Or my favorite color is somewhat very much maybe different than that of yours. So that can be taken and considered into qualitative data. Now, where we don't have any such sequence, in terms of the order preference, so that comes under nominal data. And the same, which is non-numeric, but there is a sense of preference or ordered arrangement. So there we have ordinal data. As in, we won't be able to, write formulate any mathematical idea in between women and men, or maybe blonde is greater than brown is less than black. So we cannot put it that way. But here, in terms of the ordinal data, say economic status, so that can be distributed as in an order, say low, medium, high, like that way. Or maybe education system, so that can be also brought into this structure, say pre-primary, primary, secondary, high secondary, right? So on and so forth, graduation, post graduation. So that is something what we can consider under ordinal data. Okay, so is there any concern related to like what we have looked into so far?
Sir, once can you repeat the attribute and variable?
Yeah, so attribute is something which varies from person to person or identity to identity, but is something which is non-numeric. And in a similar way, something which varies from person to person or identity to identity, but is numeric, so that is variable, right? So is it clear now? So for an example, say my favorite dish or my favorite color can be different than yours, right? But that is something which is non-numerical. So that is an attribute. Similarly, my height is numeric quantity, but that should be very much different from yours. So that is something which is variable.
Okay, so attribute is qualitative data and variable is quantitative data.
Yeah, exactly. Yeah. Okay, so let's just look into the next slide. So here we have a few level of measurements, and we have a few scales as the nominal level, ordinal level, interval level, and ratio level. So level of measurements of data often dictates the calculations that can be done to summarize and present the data and the statistical tests that can be performed. So there are 4 levels of measurements as nominal, ordinal, interval, and ratio. So let's just look into all of them. Yeah, so to start with nominal level, so here we have the data which can be classified into different categories but can never be arranged in any ordering scheme. Like I was telling you, that eye color, gender, or religious affiliation. So we can never say, this religion is greater than the other one. So there shouldn't be, any sense of ordering scheme. So that way, this is something which is coming under the nominal level. These categories are mutually exclusive or exhaustive. Now, this is something which mutually exclusive means that they might not have anything in common, or maybe they can never occur together. And mutually exhaustive means that maybe, all the categories are what all that we have into some characteristic. So say for religion, say we have, a few of the religions, available religions, uh, and that's all that we have. So there can never be any other religion other than those that we have considered. So that is the idea of mutually exhaustiveness, right? So next, let's just look into ordinal level. So this is the type of data that may be arranged in some order, but differences between data values cannot be determined or are meaningless. So like we have during a taste test of 4 colas, cola C was ranked number 1, cola B was ranked number 2, cola A was ranked number 3, and cola D was ranked number 4. So this is something, which has got some preference, or preference ordering, but there is no actual value associated with it, where we can actually be able to find the differences between the data values. Say for another example, say we can always frame it this way, that someone is more happier, than someone else, or maybe someone is looking more happy today. But we won't be able to say quantify things that, someone is 5 happy today or someone is 2 happy today. So there is no quantification available, right? So that is, but there is a sense of ordering, right? So this is what we have under ordinal level. Yeah. So next we have interval level. So similar to the ordinal level, with the additional property that meaningful amounts of differences between data values can be determined. So here the differences are quantified, so they can be determined. So there is no natural 0 point. So example, temperature on Fahrenheit scale. So of course this is the difference in the temperature, so that can be quantified, right? So this is interval. So there are few intervals, in the Fahrenheit scale when we are studying temperatures, right? So that is what it will refer to, interval scale. And ratio scale is the interval level with an inherent 0 starting point. Differences and ratios are meaningful for this level of measurements. Examples, money or height of students. So yeah, often this is very confusing in terms of the differences between interval level and ratio level. One such key point is that there is no natural 0 point, and this is something that we have here, as there is an inherent starting point, inherent 0 starting point. So ratio is something that money. So there is some sort of a multiplication of units, right? So in comparison to 1, how many do you have? So that is what you have, money. And maybe there is some inherent 0 starting point. So what if you have no money at all? So that can be there. But say for finite scale, this does not start from 0, right? So there is no absolute inherent 0 starting point. So these are the differences that we have, right? Okay, so let's just look into the next one. So now we are looking into the core idea of statistical methods. So to begin with is a central tendency. So the summary measures of central tendency enables us to draw meaningful conclusions in the functional area of operation. So the most widely used measurements of central tendency are arithmetic mean, median, and mode, right? So yeah, so what do we mean by central tendency? So suppose if we have a data set. Yeah, so suppose we have a collection of data, right? So there is some value which is known as the central value, which actually is representing the entire data set. And there are other values as well in the data set, right? Which are some are really close to that, some are far away to that central value, but all those values are what getting represented by the central value. So that those are the measures what we are going to learn in this section, such as arithmetic mean, median, mode, right? So the name of this section is central tendency. So as if there is some sort of tendency of all the observations towards the centrality, right? So if this is the central point, so all the observations are approaching towards the centrality. And the central value is something, which is actually getting to represent the entire data set. So the idea is that, the central value is the representative value of all the data set, right? So if we know the central value, then we can actually have some sort of an idea about the entire data set. So this is, the, implication of central tendency measures, right? So is this clear? Like, what is central tendency and central value? Say
Yes,
for an
sir.
yeah. Okay. So for an example, maybe, uh, say, say our prime minister is someone, who is a central value, or maybe president, who actually represents the entire country. So if the prime minister declares us, a, a state of war with some other country, so whether we want or not, whether we support it or not, we will be also in a state of war with that country. So he gets to decide, for all of us. So as in, like, he's the central value who is representing all the other values, all the other constituents in the data set, right? Yeah. Yeah. So next here we have the formula for arithmetic mean. So arithmetic mean, which is also generally called mean, is defined as a sum of all observations in a data set divided by the total number of observations. So this is the simplest of average, that we have been doing since our childhood, right? So mean is nothing but sum of all observations by number of observations. But there, in this context, there are two representations basically, which is known as the ungrouped data and group data. So that is also another aspect of looking into data, which is ungrouped data and group data, right? So by ungrouped data, what we mean is that we won't have any sort of frequency cases, right? So all the data points are considered without any the representation for that is raw. So we just have, the collection of all the data points. Whereas in group data, all the data points are sorted, right, in terms of the values and the frequencies, right? So I'll just, if I can just, so in terms of raw data, so we only have the values of X. And in terms of like frequency data or group data, we have values and corresponding frequencies, right? So here we have X1, say the first value of X, so that is X1, right? And the corresponding frequency is what we have as F1, right? Similarly, we have X2, F2, like that. Okay, so X2 and then we have F2. So now that we know from a group presentation, we know that X1 is one such variable which has occurred F1 times in the data set, right? Here, from this, we know that X2 is one such variable which has occurred F2 times in this data set. But as in here, this representation will give you the same values, but all we have is, say, X1, and say again we have X2, and say again we have X2, and say again maybe we have X1, so on and so forth, like that. So this is scattered basically, and hence the sense of this name, ungrouped and grouped. So this is much better representation of the data rather than this one where we have all the raw data scattered there one by one, right? So let's just look into the formulas. So what we have under the direct method, is this summation of xi by n, and this is summation of fx or xi fi by n. Now, I hope that you know we know like what this symbol refers to, right? Summation. Okay. And we have denotions, which is I as well, right? So first we will look into how do we denote all these values. So this is, suppose I equal to 1 will refer to, say, the first value. I mean, first address basically, right? So this is I equal to 1. Say this is I equal to 2, right? And then we have I equal to n. So I equal to 1 will refer to, say, suppose we have a street. So I equal to 1 refers to the first house in that street, right? So I equal to 2 will refer to the second house in the street, and so on and so forth till the last house, which is represented by I equal to n. So all these I values basically gives you the address or the reference, right? And the variable value, suppose I want to study family size. So X is what? Family size, right? So in the first house, that is denoted by X1. So the family size in the first house, so that is denoted by X1. The family size in the second house, so that will be denoted by X2. So on and so forth till the last house, which is Xn, right? So all these suffix that we have as 1, 2, basically are nothing but these denotions, so that we can correlate that from which address the value of the variable is coming from. So x1 denotes what? The value of the variable family size in the first house, family size, which is x, in the second house. So that is the denotion that we have, right? And summation means what? That we actually are to sum all the values. So summation xi, right? So summation xi, so this is how we write suffix I, and then this I runs from 1 to n. So starting from the initial address till the terminal address. So we consider all the addresses and the values of the variable in all these addresses. So that is the idea of summation basically. Now, why do we keep this as I equal to n? Suppose we are considering one particular street, and then we are considering some other street, right? So maybe in the first street, there are only 10 houses. So the last value of n will be 10, right? And maybe into the other street, there are 20 houses. So maybe this value of n will be 20. So because this last value can change, from case to case or street to street, so that's why in general, we write this as n, right? So we have n addresses basically. Okay, now there are 3 methods to find the value of mean. One is the direct method. This is x bar, simply the sum and then divide by the number of observations. And this for the grouped is the sum of the value and its frequency divided by n, where n is nothing but the sum total of frequencies. Now again, this n and this n is basically the same, because this n gives you the total number of observations. This also gives you the total number of observations, but in terms of the sum of the frequencies, right? So if you add all the frequencies, so you will get the total number of observations that you are dealing with. So it's just the aspect how we look into group structure and ungroup structure, right? So there is some shortcut method, so where we consider this d, which is equals to xi minus a, and a is the assumed mean. So we consider some assumed mean looking into the data set, and using this formula, so we consider that there some assumed mean, and then there will be some sort of a difference or deviation, right, from that assumed mean, which can be which can be divided by n as in a standardized deviation, right? So that is something what we consider under here. Just the same thing. just we have to accommodate one F here. So that is one more difference, how we tackle these formulas from ungroup to data, ungroup data to group data, that we have to accommodate the frequency cases. So wherever we have this suffix I, right, or into the summation, we will actually have to consider this F as well, because this F is also having I, right? In general, we have Xi and Fi, right? I mean, for which it's varying for I equal to 1. So in the first house, right? So this is the first slot, the second slot, third slot, fourth slot, like that. Okay. Okay. And there is the step deviation method, which is quite similar to this one. So here also we assume something, and then the rest of the thing is something which looks like this: x minus a by h, where h is the common width of the class intervals. So basically there are three methods. This is the easiest one and the direct method. So this is really the easiest one, and there are some other methods also to look into. Okay, so what do we have next? Okay, now I actually have to delete all this. Yeah, just a second. Yeah, so is there any concern related to the formula or maybe the presentation of grouped and ungrouped data?
My question here will be like, now how do we use this into right, like when we are let's say taking some data from the health industry, or let's say the banking industry, any of the industry, when we are picking up data, and within that data, if we have to identify the mean, right? And
Right.
it will it be like, okay, because sometimes the mean can be right into the points, or it can be a whole number, right?
Yeah.
So how do we define? Do we directly take it as a number which is going to be right continuous, or is it going to be like just we're going to take depending on the number, or mean is always, I'm just a bit not able to give you the exact question, but then what I'm trying to understand is,
Yeah.
if we are working on a data set,
Mm-hmm.
right, is it just like we plug in these formula and then like we will get what is the mean?
Yeah, I mean, in a way, it is like that. But just that we have to understand that mean is something which is related to the variable values. So we actually have to have some variable, and then only we can find the mean value of that variable. So which should be numeric, right? So if you are studying, say, what is the average systolic blood pressure? So for that, we might have different readings, coming from different people, and then we can apply, any of these methods to identify what is the mean value. So that value will be the representative value of all the data that we have collected. So, and there can be, of course, deviations from the mean value. So some readings will be higher than that, or maybe some readings will be lower than that. But at least that value of the mean will give us some idea, about the people that we have studied.
So will that be correct to say that anytime we are going to take arithmetic mean, it's only going to be worked on the variable data?
Yeah, I mean, in terms of attribute, right? So there is no scope of applying this formula, right? Yeah, but
Okay.
if it's a count data, then we can of course tackle that using the mean. So there can be a sense of mean there if it's a count data corresponding to the categories that we have. So suppose we have 4 people coming from this category, or maybe some other quantity. I mean, 10 people are coming from this category. So in that way, we can find out, like on an average, how many people are there. So all those things can be there. But of course, in terms of mean, we actually have to, deal with the numeric stuff.
Okay.
Yeah.
Yeah.
Okay. So let's just look into the next slide then. Yeah. Yeah. So this is the example of ungroup data, right? So say the inner diameter of a particular grade of tire based on 5 sample measurements are as follows. So now that you see that all these values are raw values, we only have the values, and we simply apply, the formula to get the mean. And so this gives us the idea, about the figures that we have there in the data set. So if you look into this value basically, so this is some value, which is in between all the values. So which is being able to represent all the other values in the data set as well, right? But this is another thing that what we have here is arithmetic mean gets affected by extreme values or fluctuations in sampling. So it is not the best average to use when the data set contains extreme values, very high or very low values. So suppose if one of the values, say even in this example, if say one of the values is say very high, say in thousands, then of course that gets added up in the formula, and that will somehow affect the final value of the mean. So that's why it's extremely important to tackle the outliers or the extreme values before we compute the value of the mean into our data set. And in real practice, I mean, that is what we do. I mean, we clean the data set first, and then we try to understand what are the measures that we actually have to find out in terms of the informations that we want to draw from the data set, right?
Okay.
Yeah. Okay, so I hope this is clear, how very high or very low values, extreme values affect the arithmetic mean. Suppose there are 5 students, and 4 of them did pretty bad in exam, but the last person got full marks. So he is somehow affecting the total mean value for all five of them, right?
Yeah.
Indirectly.
Yeah.
Yeah. Okay, so next we have this one, which is a group representation. Like these are the marks that that was there, and these are the corresponding figures, frequencies basically. So 6 people have got 4 marks, and 3 people have got 5, 2 of them got 6 likewise. Okay, and total number of students are 20. So by the formula, so we just have to consider this product of xi fi and then sum it up, right? So this gives us summation of xi fi. So we just have to multiply 4 into 6, 24, 5 into 3, 15, so on and so forth, and the sum gives us 122. And this gives us the total number of people that we are dealing with, total number of observations, which is 20. And then this is the formula, so we just put the value and get the answer. So which is 6.1. So on an average, for this data set, the average obtained marks is 6.1, which in a way is being able to represent all the other people that we have into the data set. So on an average, 6.1 is that marks. So anyone who has got below that is below average. Anyone who has got more than 6.1, so that can be considered as above average. Right?
Oh, okay.
Okay. So yeah. So next measure is what we have as the median. So median is the middlemost observation when we arrange the data in an ascending or descending order of magnitude. So median is such that 50% of the observations are above the median and 50% observation are below the median. So median is something, some value in the data set which actually divides the entire data set into 2 equal portions, right? Yeah, and this is something which actually the key point of median, that it does not get affected by extreme values. So it has a greater resistance to outliers. So these are the formulas. So simply median is n plus 1 by 2th value of the rank data, where n is your number of observations in the sample. Right now, if we look much deeper into this formula, so we have cases, where n is odd and n is even. So if the number of observations are odd, so then we actually use this formula, which is n plus 1 by 2th ordered observation, right? So this is ordered observation. And for when n is being even, so we have to use this one. So n by 2th ordered observation and n by 2 plus 1th ordered observations whole divided by 2. So it's basically the mean of n by 2th and n by 2 plus 1th ordered observations. Right? So this is the formula that we have. Yeah, so coming to the examples. So for ungrouped data, when n is equal to odd, so we have to arrange the data set into ascending or descending order. So this is all what we have. So first we have to order the same into an ordered arrangement. And then we have to count the number of terms that we are dealing with. I mean, number of observations. So it's 1, 2, 3, 4, 5, 6, 7, right? 7 students. So 7 is odd. So that's why we have to use this formula of n plus 1 by 2th ordered value. So n is 7. So 7 plus 1 is 8 divided by 2 is 4. So the fourth observation, right? So which is 60. So we have to count out this 1, 2, 3, 4. And indeed this fourth observation is 60. So also see that this is the observation which actually is dividing the whole of the data set into two equal parts, right? So below which you have 3 observations and above which you have 3 observations. So this is how we find the median, which is equal to 60 for this data set. All good? Okay, so let's just look into the next example, which is for n equal to even, ungrouped and n equal to even. So as we have, only the values in case of ungrouped observation. So these are the raw values that we are dealing with, and we have 10 values. So we actually have to find this, count this out. So we have like 10 values, which is even. So the first step will be to arrange the data in ascending order. So this is how we arrange them. And then we have to apply this formula. So value of n is 10. So 10 by 2 is 5. And this is 10 by 2 is 5 plus 1 is 6. So it's 5th order observation plus 6th order observation divided by 2. So this is what you have. 5th observation plus 6th observation by 2. So we have to find what is the 5th observation. 1, 2, 3, 4, 5. So which is 39. And if this is the 5th one, so this is the 6th one, so which is 41. So we have to add them up and then divide by 2. So it's arithmetic mean of the 5th and 6th ordered observation. So that way we have 40. Now, one interesting thing to look into here is that though 40 is not a value, which actually has occurred into the data set, right? The median value came out to be 40, but there is no 40 in this data set. But still, that can be considered as the median, as that is the only value, which actually divides the whole of the data set into two equal portions, right? Yeah. Equal halves, rather. So next we have a median formula for grouped ones. So this is how it looks like for the grouped structure. So in continuous group data, when we are finding median, we first construct the class boundaries in if the classes are discontinuous. So this is one, key thing that we should consider here, that if the classes are discontinuous, we first have to make them continuous. So we have to convert them into continuous. And then we have to find the cumulative frequencies and then use these two steps. So first we have to determine the median class using n by 2. And then on the basis of that median class, we will be able to locate all these other symbols that we have here, L, H, F, C, and all these, right? So L is the lower class boundary of the median class. H will be width of the median class. F will be frequency of the median class. And C will be cumulative frequency of the class preceding the median class. So it's cumulative frequency less than type, basically, right? We have two types of cumulative frequency. So it's a cumulative frequency less than type of the class preceding to the median class. Yeah, so let's just understand like what's happening here. So first of all, we have these sections, as 30 to 39, 40 to 49, all these are intervals that we have, and correspondingly we have number of students into these intervals. So this is examination marks. So we have 8 students, those who have got in between 30 and 39. We have 87 students, those who have got in between 40 to 49, and 190 students in between 50 to 59, and so on and so forth. So this is the formula that we have to apply. So first of all, we have to convert these values into class boundaries. So previously, if you may see that, these values were discontinuous, as because, like we have considered from 30 to 39, but what if, someone gets more than 39, but less than 40? So if someone gets 39.5, so what about that? So that is not being considered. So there is a break in that, right? So in that way, we have to convert these class intervals into class boundaries, which will be having a sense of continuity there. So how do we do that? We actually subtract 0.5, from the lower interval, and add 0.5 to the upper interval, so that it gets converted into these class boundaries. Now, if we are measuring from 0, so of course there is no point of subtracting 0.5 from zeros, which will take into the negative scale. If we are not working with that, then it's fine, absolutely fine. Or maybe if we already have something which is 100, say if the last interval is something like 90 or 91 to 100, so there is no point of adding 0.5, which will make 100.5, which is out of the scope of obtained marks. So in those cases, we can actually exclude this 0.5 consideration of this 0.5, but other than that, this is the procedure, like we convert this into class boundaries, right? Now the other thing is that as because these are the intervals, so these are the intervals basically, so we don't have any provision in terms of considering the intervals into the formula. So for that, what we have to do is we have to consider the midpoints. So these are the midpoints that we have to consider. So how do we get the midpoints? So it's just that we have to sum these two and then divide by 2. So this will give you the midpoints, and these are the frequencies, which remains the same, right? So this midpoint is that central value of this class. So this midpoint is being able to address or represent the entire class boundary. Okay, so this is what we have as the frequency values, and if we sum the frequencies, we have total of 905 students. And this is what we have as cumulative frequency less than type. So less than type means that we have to add from the very top. So for 8, corresponding to 8, we will have 8, and then we will have 8 plus 87, which is 95, and then 8 plus 87 plus 190, which will be 285. And now that we know the sum till 190 is 285, so we can just add 285 plus 304, which makes to 589, and then 589 plus 211, which is 800, so on and so forth. Mind you that this the sum of the frequency total will be exactly equal to the last entry of the cumulative frequency. Now, what does this actually mean is that how many, as because this is less than type, right? So how many of the observations are there less than to the upper boundary of the class? Now, if I'm to find less than something, so of course, the one that I've been considering is something which is, more or upper value, right? So less than type, right? So the type itself needs to be more so that we can consider less than of that type. So of course that refers to this 39.5. So the question the idea that this gives you is that how many of the observations are there below 39.5? So that is 8. Similarly, how many of the observations are there below 49.5? So of course that will be those who are having those who are there in like 39.5 to 49.5, and also that we have to consider the previous class as well, because that is lesser than 49.5. That's why things are getting added up, right? And finally, if we consider this value 99.5, so how many people are there, how many students are there below this value? So that is all of them, right? All of them. So that is the sum total basically. So that's why we have this as 905. Similarly, there is this idea of cumulative frequency more than type, which will give you that the number of values which is more than the type. Now, if it has to be more than, so of course we are talking about the lower boundary, right? The type itself is lowered. So, above which we are more, which we are we are considering, right? So how do we find it? It's just the same procedure, we just have to sum from the bottom now. So instead of 20, corresponding 20, we have 20, and then 20 plus 85 is something what we write there, and then 20 plus 85 plus 211. And of course, the first entry into cumulative frequency more than type will be same as the sum total, which is 905, which again gives us this answer that how many of the students are there, those who have got more than 29.5. Of course, all of them, because this is the least value, right? Okay, now the main thing here is to find the class, the median class, as because if you see this formula, all these other denotions have got this thing in common: median class, median class, median class, median class, right? So this is this important thing to find the median class first. And how do we do it? So using this n by 2, right? Using this n by 2, so which is 905 by 2. So this is, this is the value which actually corresponds to which class. That is what we have to find. So let's just look into this formula once more, So here this n by 2 basically, so this is the n by 2 that we want to find, which determines the median class in the formula, right? So now we have to see which is that value in the cumulative frequency less than type column, which actually contains this value 452.5, right? So we have to see which is that value which contains this 452. Do we have a 452.5 in 285? No. So do we have 452.5 in 589? Yes. Do we have 452.5 in 800? Yes. So the idea is which is the value in cumulative frequency column which immediately contains this value. So immediately contains will be this value, corresponding to which we will refer to as the median class. So this is the median class, right? 59.5 and 69.5 will be the median class. So now we have been able to locate the median class, and of course, which implies that the value of the median will be lying in between in this class, right? Somewhere lying here inside this class. So is this understandable? I mean, so far?
Yes, sir.
Yeah, okay. So let's just look into the next one then. So this is the value that we have, found out there, and then this corresponds to this class. So in the formula, this L refer to the lower class boundary of the median class. Now that we know this is the median class, so the lower class boundary will refer to 59.5. So we just substitute this value 59.5 in place of L, right? So F correspond to what? The frequency, class frequency of the median class. So again, let's just have a look. What is the class frequency of median class? So this is the median class, right? So this is the class frequency. So that way we have to put this 304 here, right? N by 2 is something that we already know. And then we have this 10. So this is the class width of the median class. Now here we have, all the class boundaries having equal width, but it might well happen that, all the class boundaries are not of equal width. So in that case, we have to look into what is the width of the median class. So that is 69.5 minus 59.5. So that is this 10. And then we have this 285, which will be the cumulative frequency less than type value just preceding the median class. So this is the median class, right? So this is the cumulative frequency less than type value of the median class, and preceding to this value will be this value. So this is what we are talking about. The cumulative frequency less than type value just preceding the median class, right? So this is the value we are talking about, 285. Yeah, so next just we have to put the values, and this is what we get as the answer. So it comes out as 65. So 65 is the median marks. So below 60, so what is the implication of this marks? Basically, so 50% of the population is below this 65 and 50% of the population is above 65. in this examination. All good?
Yes,
Yeah.
sir.
Yeah. Okay. So then this is the last thing that I guess we are going to cover today. So this will be mode. So mode is the value which occurs most often. So it has a maximum frequency of occurrence. Mode also has resistance to outliers. So this is same, as median. So this has also some resistance to the outliers. So mode is a very useful measure when you want to keep in the inventory the most popular shirt in terms of collar size during festival season. So basically the observation which has occurred or repeated itself for the maximum number of times, so that is referred as the mode, right? So in a few problems in real life, there will be more than one mode, such as binomial multimodal values. In these cases, mode cannot be uniquely determined. So there might be, cases where you have two modes or maybe many modes, so that is referred as bimodal or multimodal. So we will look into that in detail when we will tackle the probability distributions, right? So yeah.
I have one question.
Yeah, sure. Tell me.
Yeah. So now let's say for mode, right? And when we are doing in any kind of right analysis, right?
Yes.
In actual analysis, or for example, we are finding out data in the data where number of times, right, blood pressure has been. So there is a number of blood pressure which has been recorded into a data set.
Yeah.
And in that data set, if we say that there are, because the population of people where the blood pressure has been taken varies a lot. And in that, like, there are bound to be outliers,
Right.
right? So in that case, will I be correct if I say that it is better to take mode than to take mean or median?
Yeah, absolutely. I mean, of course, this will depend on the study that we are looking into. So, in this example, of course, mode will be one such valid measure to consider, because maybe a few of the observations will actually have extreme blood pressure, maybe extreme high blood pressure or extreme low blood pressure, which will affect the average blood pressure for all the participants, right? So for mode, I guess this will be much suited in terms of what will be the most, that value which has occurred mostly in terms of the data set. Yeah, so it makes sense. So of course, yeah, there are cases, and it completely depends on the experiment that we are taking, and also the aspect that we are looking into. So accordingly, we will have to justify whether mean or median or mode will be the best measure to consider for. Practically, I mean,
So
all this. Yeah, tell me.
if I'm understanding correctly, like as a data scientist, uh, whenever we need to be focused, like based on the data that we are working on, whenever we need to right work on averages, we probably look at the mean. And whenever we want to look at the exact center point where the data is being divided into two sets or two
Yeah.
sections,
Mm-hmm.
that time, like, we consider the median. And
Yeah.
the mode we consider that when we know that, okay, in our data set, right, there are bound to be, right, a strong what do you say, a strong outlier
Yeah.
data set with like the variant of outliers being higher. Mode will be the best option to decide the what do you say, the correctness or accuracy for the future prediction. Correct?
Yeah. In a way, so it can be median as well, or mode even. So yeah, in case we are having many outliers, so there we can actually use mode or median instead of mean, according to the case that we are considering.
Okay. Yeah.
Yeah.
Yeah. Thanks.
Yeah. in practice, as a data scientist, we actually want to look at the distribution of the data set. So in that context, we will be able to identify whether that particular data set is a symmetric distribution or it has got some skewness associated with it, which actually gives us much things to understand. And accordingly, we have we can actually tackle those situations. I mean, like what we encounter with. Yeah, we have examples of that even, just after this. So yeah, so let's just move on to the next slide now. So this is the comparison, of mean, median, and mode. So before that, we have this as well. So suppose there are 10 flashlight batteries, find the mode. So this is what we have to find, in terms of the life in numbers of hours. So which is the one, occurring for maximum number of times. So it's 342, I guess, right? So 342, 342. So it has got maximum number of occurrence. So hence, this occurs 5 times. So that's why this is the mode. Right? So next we have this sense of comparison in between mean, median, and mode. So mean is something which gets affected by extreme values. Sorry. Yeah, so median does not get affected by extreme values, and mode is also not affected by extreme values. Now for mean, this can be treated algebraically. That is, means of several groups can be combined, right? So there is something called a combined mean, where we have, if we know, the mean of different data sets, we can actually find what will be the mean of the whole of the data sets considered together. So which is called as combined mean, right? And here but for median, it cannot be treated algebraically, in a sense that, medians of several groups can never be combined, right? So that is there. And same for mode as well. So modes of several groups can never be combined. So these are the basic differences of mean, median, mode. So according to the situation, we always, in general, we try to fit in to the measure of mean. But if that does not work perfectly, or gives not, I mean, if it's there, having some problems with the extreme values, presence of extreme values, then we can consider median or mode, depending on the situation or the problem that we are tackling. Right. So next we have quantiles. So do we have time to look into quantiles today, or we should keep that for the next class?
Spandana, are you okay?
Yes, sir. I'm okay.
Okay. So
Half an hour.
okay, so let's just get into quartiles today. So in general, we have quantiles, which basically can be, divided into quartiles or deciles or percentiles. So when the observations are arranged in increasing order, then the values that divide the whole data set into 4 equal parts, that are called quartiles. So likewise, I mean, when we studied median, so it used to divide the whole data set into 2 equal parts. So quartiles are those values which actually divide the whole data set into 4 equal parts. And we have the first quartile denoted by Q1, second quartile denoted by Q2, and third quartile denoted by Q3, right? So now it is to be noted that 25% of the data should fall below Q1, 50% of the data should fall below Q2, and 75% of the data should fall below Q4. I mean, sorry, Q3. And then in the similar approach, we have deciles. So where we actually have 10 equal parts. So deciles are, when the observations are arranged and the values that divide, the whole data into 10 equal parts. So that is called deciles, right? So yeah, this is mistaken. This is deciles actually. So, these values are denoted by D1, D2, D3, so on and so forth, Dn, I mean D9, right? And it is to be noted that 10% of the data falls below D1, 20% will fall below D2, and 90% will fall below D9, right? Similarly, we have percentiles. It's just the same thing, same approach where we actually divide the whole data into 100 equal parts. And for that, we need like 99, I mean, uh, segments basically. So 99 points basically. So which will divide the whole data into 100 equal parts. And that way we have P1, P2, P3, so on and so forth, P99. So 1% of the data will fall under P1, 2% will fall below P2, 99% will be falling under P99, right? So is this idea okay?
Yeah. So if I understand correctly, it will be like so when we talk about quartiles, it's like every quarter.
Yeah, every quarter.
And when
Yes.
we talk about deciles, it's like every point, whereas like a
Yeah.
decade, right? Every 10th point.
Yeah. It's
That was
just how we may look into decimals,
okay.
So yeah.
Okay. And then percentile is obviously like it's the 100 of
Yeah.
that. Okay.
Yes. So this is the distribution that we have here. And you can see that these are the values, that we have in terms of percentiles, deciles, and quartiles. So first, let's just start from the bottom. So in terms of quartiles, so this is the first quartile, this value. So below which we are having the 25% of the data set, right? This is the 25, first 1/4 part. And then the next quartile, which is same as the median, because below which we will have 50% of the data set, right? So what 25% we had before this one, Q1, right? And furthermore 25% what we have in between Q1 and Q2, so which makes to 50% below Q2, which is the median as well, right? Similarly, the third quartile is here, below which we have 75% of the whole data set. So this is the whole 100% data set. Just refer to this point, below which we will have 75% of the data set, and above which we are having 25% of the data set. So that is your Q3. So this is your Q1, this is your Q2, which is same as the median, and then this is your Q3. Next, let's just look into deciles. So here we actually have divided the whole of the data set into 10 equal parts, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So there are 10 sections. There should be 10 sections, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, right? So 9 points, which is giving 10 sections, 10 equal sections, right? So below this D1, the first decile, we will have 1/10 of the whole of the population, right? So below D2, we will have 2/10 of the whole of the population, basically. Next, we have 3/10 of the whole of the population, right? Under D3. Similarly, under D7, we should have 70% of the whole of the population, which is 7/10 proportion of the whole of the population, right? So out of 10 equal parts, we have considered till the 7 equal parts, and 3 are left. 1, 2, 3 are left below this. Similarly, in percentiles, we actually have divided, the whole of the data set into 100 equal parts. So below this, we have 10%, below this, we have 20%, 30%, 40%, 50%, 60%, like that. So mind you that this is something, which is actually equal. So whether it be it median or the second quartile or the 5th decile or the 50th percentile, all of them are being equal to the median, which is the middlemost point of the data set. This is what you have to realize, right? So like what we have here, the lowest value here, the highest value there. So median is something, which is dividing the whole of the data set into 2 equal parts having 50% and 50%. For quartiles, we have like 3 measures, Q1, Q2, Q3, which is dividing the whole of the data set into 4 equal proportions. So here we have 25% of the population. Here we have 25% population, 25%, 25%. So below Q1, we have 25. Below Q2, we have this 25 plus this 25, which makes 50%. So again, this Q2 is nothing but the median. And Q3 will be 25 plus 25 plus 25. So that's 75% of the data set, right? Similarly, for the deciles, So each of these blocks has 10% of the observations, right? So say the third decile, which is 1, 2, 3. So up till here, we should have 30% of the data set. So this is the fifth decile. Up till here, we should have 50% of the data set, which is same as the median value. I guess this actually helped in terms of understanding the percentiles and the deciles. And also you may see that, the values can be same basically. I mean, the value of Q2 can be same of that of X curl, which is the median, which is same of D5. Or maybe here, this is D5, D6, D7. So in between D7 and D8, you will have, 75%. So Q3 will be somewhere here in between, right? So that they can be overlapping as well. Okay. So this is what we have in terms of idea of skewness. So once we get, any data set, we try to understand the structure of the data set, whether it's symmetric or positively skewed or negatively skewed, using all this mean, median, mode, all the measures of central tendency. So here in symmetric distribution, what we have is mean equal to median equal to mode. So which means that all three measures are equal, and this is nice bell-shaped, symmetric curve. So this point is basically dividing the whole of the data set into two equal parts, right? And there is equal concentration into the two halves that we have considered. But if we have something somewhat like this, okay, now how do we identify that this is mean or median or mode, right? So of course, what are we plotting? So we are plotting on the x-axis, we are plotting all the values of the variable, and on the y-axis we are plotting the frequencies, right? Frequency densities or frequencies, so we are plotting that onto the onto the y-axis, right? So this point is the highest frequency or the frequency density that we have, right? This point. So corresponding to this, we should have the value of the mode, right? Again, sorry. So if we are trying to consider the median, so this is the spread of the data, right? This is the minimum point and this is the maximum point. So median should be that point which actually divides the data into two equal parts. So again, this point is what it is referring to be as a median, right? And mean, so if we consider the concentration of the whole of this data set, of this diagram, so the mean center should be somewhere around here. The mean concentration will be somewhere in here. So three of which being the same point for a symmetrical distribution. For a positively skewed distribution, it's actually easier to identify the value of mode, because this is, the highest density that we have. So corresponding to which we will have this value as your modal value, right? This is as the mode. And then we can see which is the median. So which will be the middlemost point of the data set, which will be here. Now, if you have a triangle which looks like this, so, the mean concentration will be somewhere around here, like what we had from geometry, right? So the mean concentration is there. So mean will be somewhere around here, right? So here we have mode is less than median is less than mean. So then we have a case of positively skewed distribution. Similarly, for negatively skewed distribution, again, it's really easy to identify the mode. So this is the mode. Then the median will be, the middlemost point, and mean. So it's just the reverse triangle that we are dealing with, right? So this epicenter, this is, where you have the maximum concentration. So this will be the mean value. So this is how we have, positively skewed distribution or a symmetric distribution or a negatively skewed distribution. Right? So is there any concern or questions, related to this?
No.
Okay. Spandana, all good?
Yeah. Yes, sir.
Okay. Okay. So next we have measures of dispersion. So yeah, let's just look into measures of dispersion as well today. So this is what we have as measures of dispersion, which help us to interpret the variability of the data, that, how much homogeneous or heterogeneous the data is, which the other way is looking into, how much data is spread around the central value. So if we refer to, the diagram of the central value, so how much, a data point is differing from that central value, whether it is much closer to it or maybe far away from the central value. So that is what we study or look into here under measures of dispersion. So these are the measures that we are going to look into: range, interquartile range, standard deviation. These are the three mostly commonly used, measures of dispersion. So range being the simplest of them. So range is nothing but, the difference of the highest value and the lowest value, which actually gives you the idea of the spread of the data set, right? So the range is the spread of your data from the lowest to the highest value in the distribution. It is commonly used measure of variability. So this gives us some idea about the spread of the data set, right? So which actually gives us this information about the variability that we might have in terms of the spread. So this is the formula. This is the easiest measure to calculate. Next, we have interquartile range. Now, this is very interesting. Interquartile range, which actually is dependent on the quartile measures that we have looked into before. So interquartile range, IQR, so is the difference between the third quartile and the first quartile. So range computed on middle 50% of the observations after eliminating the highest and the lowest 25%. So we actually let go, the highest 25% and the lowest 25%. So we just see, the spread or the range in between Q3 and Q1. So that will actually give us, some information regarding the spread of the data set or the variability of the data set. So this is Q3 minus Q1. So if this is the data set, first we have to arrange it, and then we have to calculate Q3 value and Q1 value. Now there are ways to do that, of course. So so this is the 14 came out to be as a third quartile value, and 11 came out to be as a first quartile value. So the difference of that is 3. So which gives us some sort of an idea about the variability which is there in the data set, right? Okay, so next we look into the standard deviation. So standard deviation forms the cornerstone for the inferential statistics. So this is very much important in terms of inferential aspect. So define standard deviation, we need to identify or define another term, which is the variance. So this is how we denote variance as sigma square, and standard deviation is nothing but root over of variance. Okay. So again, there are like 2 versions of this in terms of population and sample. So in terms of population, we denote this as sigma, and sample, we denote this by S. And this is the formula of summation of x minus mu whole square divided by capital N. And here we have summation of x minus x bar whole square divided by n minus 1. So capital N denotes the total number of observations in the population, whereas small n denotes the total number of observations in the sample. So here there is some change in terms of the sample when compared to that of the population. And why is this change is something that we are going to look into later on of this course, where we will understand the concept of unbiased estimator. So then we will be able to look into this change. So this is what we have as a formulation, and then let's just look into a few of these examples. So as because there is always this value of mu or x bar, so we actually have to find the sample arithmetic mean or the population arithmetic mean in terms of finding the sample standard deviation or the population standard deviation, right? So as because we have these values, so first we find the mean age, right, which will be nothing but the addition of all the values divided by the number of observations, and which comes out to be as 28.47. And then we have to calculate this standard deviation using the formula, using this formula. So these are the calculations that we have to do. So x are the values that we already have, and then we have to find the deviation of x minus x bar. So once we have that, then we actually have to square that, because we are considering the sum of the deviations, squared deviations, right? The sum of the squared deviations. Now, why do we need to square them? Because, this actually gives us some relative zoom in effect into the data set. So the relative differences gets maximized. Also, if there is any, negative values present in the data set, so that it doesn't cancel, each other out in terms of taking the sum. That's why we consider instead the squared sum. So this is how we consider the squared sum. And then if we add this, so this gives us summation of x minus x bar whole square of that. Right. So this is what we have as 311.72. So this is what we have already. And then n minus 1 will be 14. So likewise, this comes out to be 4.72. So this, what does this mean? So we are calculating the difference of each observation from the mean. So on average, there is a difference of 4.72 considered from the mean. So which is what they have put up here. As such, we can interpret the value of 4.72 as the average deviation between the individual observations and the mean. So the mean, what it came out to be 28.47. So that is the, that is the central value, what we could locate. But from that central value, on an average, there is a deviation of plus minus 4.72 in terms of all the other values that we have considered here into the data set. Right? So that is the idea of standard deviation. Yeah, so this is the last thing that we have under measures of dispersion, coefficient of variation. So this is actually a ratio of standard deviation to mean. So coefficient of variation, does not have any unit as it is a ratio. And it is a measure of relative variability. So we see that, in terms of the variability identified from the mean, right? So to that of the value of the mean itself. So how much variation is there, which gives us this coefficient of variation, right? So investment decision example. So coefficient of variation is useful for comparison of variability between two variables or two tests, if it can be used for comparison only for ratio scale variables. So suppose if we have average value, so this actually gives us, the idea of the coefficient of variation, higher the coefficient of variation, so lower will be the consistency, right? So lower the coefficient of variation. So if this is a coefficient of variation, right? So higher this will imply lower, lower consistency, right? So suppose if we have like two batsmen, with a different batting average or different scores, and maybe there is this batsman A who is having, higher average than batsman B, but the coefficient of variation for batsman B is somewhat much lesser than that of batsman A, which implies that batsman B is much consistent in terms of his performance, even though batsman A is much better player in terms of the average, right? Yeah. So is there any question?
So one more example for coefficient of variation.
Coefficient of variation, yeah. So yeah, there can be, a few. Suppose two students are have some, obtained marks in terms of their performances, right? So maybe someone is having a better average, right? But altogether, if we consider the coefficient of variation, so maybe for the other student, the coefficient of variation is much lesser than that of the first one. So which implies that the second student is much more consistent in terms of his performance, right?
So if I understand correctly,
Yeah.
right, it's basically like, let's say how consistently the student one is performing and how consistently the student two is performing, right? And
Yes.
same way, how consistently the batsman one is performing and how consistently
Yes.
batsman two is performing,
Yes.
right? Will be shown by the coefficient of variation.
Yes, exactly.
And the more variation somebody has,
Mhm.
right? Just to have an idea, more variation if somebody has, will it be better or less variation if somebody has?
So
Will it be better?
if someone is having more variation, so that means there is less consistency, right? So
Correct.
I mean, these are like complementary events, right? So if you have more variation, so of course there is lack of consistency.
Hmm.
Whereas in if you are more consistent, so of course there will be less variation. So even though, if we are taking a consideration of that example of batsman 1 and batsman 2, so even if batsman 1 is a better player in terms of the average, right?
Hmm.
But he's not that consistent. Maybe if we look into, last 4 innings, maybe, I mean, he has scored like all, for the 3 of them, he has scored all single digits, maybe. And maybe, in the fourth match, he has scored a 150,
Oh,
right?
yeah. So
Which,
I get it now. So
yeah,
let's say now, right in Mumbai, we had right heavy rain on a single day,
yeah,
right? We had covered the rain for almost half the season.
yes,
So that would not be right considered as the great right one of the best days to calculate how much rain does Mumbai gets. So
yeah.
because the variation is so high in a single day, if like you have so much of rain coming in,
Mhm.
and we can't define with that okay, every day Mumbai is going to get such heavy rains.
Yeah,
Yeah.
actually,
Okay. Yeah. Yeah. Got it. Got
yeah.
it. Spandana, you also
So
understand.
there is some example, related to this. Oh, it just got started from the beginning. Just a second. Yeah. So there are few examples, in terms of the mutual fund A and mutual fund B. So if two mutual funds have different expected returns and standard deviations, so expected return, so higher the return, so it's a better mutual fund, right? So that is something what we have to accept. If
Correct.
mutual fund A is giving us 15% return, whereas mutual fund B is giving us 10% of return, then of course mutual fund A will be much beneficiary for us, right? In terms of performance. But the standard deviation of the returns of this on these mutual funds is 10% for A and 5% for B. So now if we try to find which is a better investment, so an investment will be, only looked as a better one, which has got less, risk, right? Of course, return is important, but less risk is also important, even more important than greater returns, right? So for a risk average investor, mutual fund B would be better investment because here the return is 5% by 10%, which is 0.5, right? The SD is 5% and the corresponding mean is 10%. So 5 by 10 is 0.5. So we have 50% of, the variation present in mutual fund B. Whereas in mutual fund A, though it is giving us 15% of return, but as because it has got a higher variation, so 10% of standard deviation divided by 15% of its return, so that gives us 0.67. So there is a 67% variation in mutual fund A, right? So of course, for a better investment perspective, this is having much lesser risk present. So of course, then this will be much preferred. Mutual fund B should be much preferred. Is it clear now?
Yes.
Yes.
Yeah. Okay. So yeah, next let's just look into scatter plot as well today. So I'll just start with the brief idea of scatter plot. So a scatter plot is a graph, which is a type of plot or mathematical diagram which uses the Cartesian coordinates to display values for typically two variables for a set of data. So by these two variables, what we mean is a pair data. So if we have a bivariate data, right? Bi means two and variate means which is varying accordingly. So for x1, we have corresponding value of y as y1. For x2, for the second entry in the value of x, x2, we have corresponding value of y as y2, and so on and so forth, right? So if we plot all these points, using these Cartesian coordinates, where we consider the set of values of y as the dependent variable and the set of values of x as the independent variable, so that plot will give us some sort of an relationship. It can give us some show relationships between the two numeric variables, and the dots in a scatter plot not only report the values of an individual data points, but also patterns when the data are taken as a whole. So if we consider all the data points that we are working with, suppose n pairs of data. So if we plot, suppose we are dealing with 100 paired data. So if we plot all of them, so that can result in a particular relationship, which will be helpful in terms of understanding the association between the two variables, or the degree of association between the two variables. So this is the example of scatter plot. So this is a strong positive linear, so we have a linear relationship. So what we are plotting is the values of x along with x-axis, and values of y along y-axis, and each of these pairs are x1, the coordinates will be x1 y1, says this is x2 y2, x3 y3, this is x4 y4, so on and so forth, right? So all this will result us in some pattern, right, using which we will be able to find the degree of association between the variables. So here we can see, as the values of x increases, the corresponding value of y is also likely to increase, right? So this is having a strong positive linear correlation. Say temperature and pressure are somewhat strong, having a strong positive linear correlation. So if we increase the pressure, maybe the resultant temperature will also increase, like that. So if we decrease the temperature, decrease the pressure, maybe there will be decrease in the temperature as well. So this is strict, so if x is increasing, y is also likely to increase, right? Y will also increase. But similarly, if we have something somewhat which is down slope, this is which is here we are having a up slope like this way, right? So if something we have on somewhat like down slope, as in like what we have here, so that will be denoted as strong negative linear correlation. But here, instead of strong, we have moderate. Why do we have this? Because the spread of the data in comparison to this one is much more, so there is more scatteredness in terms of the presentation that we have if we try to fit a linear line. So fitting a linear line means what? That we want to pass a linear line, right? I mean, on these points, data points, such that most of the points are covered, so that we can be able to draw the line using most of the points. But here it is somewhat impossible, because this is having a larger spread. So in a way, it's always negatively correlated, of course. So which means that with the increase of the value of x, the corresponding y is likely to decrease, right? So if you increase x, from so if you increase x, the corresponding value of y is likely to decrease, right? Suppose, see, compare this point and this point. So this is your x value. Suppose if I increase this to this, the corresponding y value, the height of this data point got dropped, like that. So if I'm considering this one, see, the next data points are dropped. Of course, there are I mean, few exceptions, but that's okay. I mean, altogether, if you consider the trend, so this is what you should get. So which is moderately negatively correlated. Now, if we have a pattern which is somewhat not having a linear structure, which is giving you a curve or a parabola, hyperbola, like that structure, a curvilinear structure. So in that case, we have a strong bond, because the scatteredness, the degree of scatteredness is not that much, the spread is not that much, but still this is something not linear as well, because by no means we will be able to pass a line using the most of the points. So if we consider this like the line like this, of course the whole of this part is not considered. If we consider like this, then of course these two parts are not considered. if we are considering like this, so of course, we will have to consider a curve which will be able to pass through most of the points. So that way, this is non-linear relationship. And here we definitely we don't have any pattern, from which is identifiable pattern, from where, we can infer that there is no linear correlation between the variables. Right. So, I mean, by no means we will be able to fit a straight line, over all these points. So this is the idea of scatter plot. Okay. So next we have the degree of correlation. So if we have strong positive correlation, the value of y increases as the value of x increases. Strong negative correlation, so the value of y decreases as the value of x increases. So you can think of this as directly proportional and indirectly proportional cases. So next we have weak positive and weak negative, right? So that will be the value of y slightly increases as the value of x increases. This means that the value of y will either increase or remain the same. By no means it is not likely to decrease. So with the increment in the values of x, the corresponding values of y will either increase or remain the same. It won't decrease, So that is what we have under weak positive correlation. Similarly, for weak negative correlation, the value of y decreases slightly as the value of x increases. So if with the increment in the values of x, the corresponding value of y either remains the same or gets decreased. So by no means it gets increased. So that is what we have under weak negative correlation. I mean, the basic difference between weak and strong is that here you have the impact of the positive correlation much noted in terms of there is no rest period, or there is no pause in terms of the positive growth or the negative growth, right? But here there can be a sense of pause, as in like the y can increase slightly and then maybe it actually doesn't increase for some values of x, and again it gets to increase for further values of x, and so on and so forth like that. Complex correlation, so here the value of y seems to be related to the value of x, but the relationship is not easily determined. So if there is some pattern, but which is which is not that easy to identify, so that will be something which can be referred under this complex correlation. And no correlation, so there is no demonstrated connection between two variables, right? So I mean, no correlation, it's better to say no linear correlation, right? So all these are under the linear part actually. So these are the diagrams that we have. So so day of planting, and this is height. So as the number of days gets increased, the height of the trees actually gets increased, right? So this is what we have as strong positive correlation. This is weight and kilometer runs per week. So as the number of weeks increases, so weight actually gets to reduce like this. This is a strong negative correlation. Customer satisfaction. So here, what we have is age and the satisfaction score. Okay. So here we see that with the increment in age, the satisfaction score is much likely to be on the higher side. But there are exceptions to this. Someone who is below 30 is, like someone who is, I mean, you can see this as someone who is, as at the age of 45 is not that satisfied. Satisfaction level is below 30, right? And someone, who is, I mean, on the verge of 30, say 29 or something like that. So he's having a greater satisfaction. So there are exceptions, but in a way, altogether put it, I mean, we can put it this way, that there is a increasing trend. So with the, I mean, this is nothing trivial. I mean, this is just, like studied from a data set maybe. Okay. So this is something which is having a complex correlation, expenditure on entertainment. So with the increase of age, this is having, entertainment expenditure keeps on increasing. And then after that time point of, some time point, it actually drops down like this. So this is having some sort of an complex correlation. So maybe there is some other structure than linear correlation, which will be able to fit this right. And this is inconclusive in terms of finding, any pattern there. So previously we actually could find a pattern, but it was not that easy to predict or fit that using a straight line at least. But here we are quite not being able to identify if there any pattern exists at all. So this is internet usage, and then you have hours per week. Okay. So I mean the work done or something like that maybe. Yeah. So, yeah. So this is all that we have. So there is some examples of this. Arm length on grade 11 example. So this is a scatter diagram, like we have already looked into this. So this is height and this is arm length. So as and when your height will increase, of course your arm length is supposed to increase as well. So this is what we have here. And on the basis of these degrees of association, there is this measure of correlation and correlation coefficients, which actually measure the strength of the linear relationship between the two variables. And where 0 will indicate, that there is no linear correlation, and anything positive will denote that there is a positive correlation. Negative will be value lesser than 0 will be implying that there is a negative relationship, like that. Yeah. So we can so this is the to identify the correlation coefficient, which is time consuming. So data are often plugged into a calculator, computer, or statistic program to find the coefficient. So this is how the structure of programming and data science, all this come into play. So once we know, identify the data that we are working with and all the necessary steps to identify the patterns and all, then for any results we can utilize any of the statistical programming tools to find out the values of the variable. And then again, corresponding, I mean, on the basis of that, on the basis of our outcome, we actually have to infer about how it is being applicable to the data set. Yeah, so this is all what we had for today for descriptive statistics. So I'll just stop here then. Before that, if there is any question.
No, I mean, it was great. Spandana, you have any questions? Anything, any clarification?
No, sir. For now, okay, understood.
Yeah. Okay, so I'll just stop sharing then. And thank you everyone for joining me today. Yeah, thanks.
Okay.